So far, you should at least be somewhat familiar with indices or powers, that is to say something is being squared or cubed or so forth. And we can use that to find, say, a value of x. Like if we had that 5 squared equals x, you could say that therefore x is going to be 25. Or if x cubed is 8, you could cube root the 8 to just get what x is, so it'd be 2. However, what if your x is the power itself? It's the power, the indices that you don't know. We can't do the x root because, again, we don't know the value of x. So what we have to use instead is something called logarithms. If we were to have a general formula that a to the power of x equals b, we could say that log to base a, and then b in brackets, equals that power of x. So for an example, if we had 2 to the power of x equals 3, we could say that that's going to be log, and you put a small 2 down here, and then in the brackets you put 3. That would equal x, which, if say we were just to go to 3 decimal places, in this case would be 1.585. In order to do this, you should have a button on your calculator, which will look something like this with log, small box, and a big box, with the small box just being the base, and the big box being what you're going to put in the brackets. There is another one, which is just log on its own. For this, that is assuming that 10 is the base. Basically, previously, when this prior button here wasn't a thing, people would just have to do logarithms to base 10 regardless and manipulate them from there. That's why that's just a regular log function. It's still there because we can use it, whether we need to just make log base 10 anyway, or if maybe the question is just presenting you with log full stop without any specified base, we can use this, or at least interpret that, okay, this is a base 10. Knowing the base and then maybe an answer, we can then also work backwards to find an x if that's inside the logarithm brackets. If we had log base 7 of x equals 4, well, working this backwards, you take the base first, that'll be the 7, and then put that to the power of whatever's after the equal sign. So that'll be the 4, and that will equal what was in the brackets, so in this case your x, which in this case would be 2,401. Now it might be that rather than just solving, you're just looking to make something the subject. Say you had this, where 9 to the power of y equals x minus 10, and you just want to make y the subject. What we'll do is we will take logarithms because that's how we can solve or at least bring down power. So we'll have y equals, that'll be log base 9, but here what goes in the brackets? It has to be the entire expression in one bracket. You can't take a logarithm of each individually. So making y the subject would look like this in this case. Now then, if we are trying to solve using logarithms, we may wish to manipulate them first. We may wish to either combine them or rewrite them in some way. If, say, you had 2 logarithms that you want to add together, and to be clear here, they have to be to the same base and the same coefficient, or ideally no coefficient at all. In that event, we can say that this would have the same value of another logarithm to the same base, but then these 2 numbers here times together. So if it was log 4 plus log 5, that would be the same as log 20. Instead, if we were to minus them, well, if adding is timesing, then minusing is going to be dividing. Again, it has to be to the same base and same coefficient. If instead your other letter here is a power, so log base a of b to the c, what we can do is we can bring this power out in front and say that's the same as that c value and then log of just the b. It may actually be that you're more often going to do this rule backwards to get rid of the coefficient so that you can do one of these first two, because again the coefficients need to be the same here. So if this had a coefficient here and this didn't, you could bring that coefficient up inside the bracket. So it's now a power and then they'd both have, well, no coefficients. That's the same as being the same. And lastly, this fourth one is nowhere near as common, but it is still a thing we just want to be aware of. And this is where we can change the base. Again, for these rules above, you need to have the same base. So if, say, instead wanted to make it a base of c, so log base c of b, you can do that, but you'll then have to divide by log base c of a. So this original base is now in the bracket in the denominator of another log of the base that you desired. One other principle just to mention here at the beginning is in a specific term which can have x to it as a power, this being e. Now, the real importance of e is going to be explored more when we get to differentiating. But just to say here, it's a specific constant in maths. You will have it as a button on your calculator. You may have to select shift or alpha to reach it first. But here, if we had e to an x, and then we want to take logarithms, so e would now be the base, and then of y. Because e is so special in maths, it has its own shorthand for the logarithm, which is the natural logarithm. So ln, which is in turn another button on your calculator. So if you see ln, this is just this constant e as the base of any other regular logarithm, treating it as you would have before. Now, if you just wanted to sketch these, if you were to sketch the graph of y equals e to the x, that would look something like this. We're very close to the x-axis on the left-hand side in the negative. It's always tending towards the x-axis, but it's never going to touch it. It then crosses the y-axis here at 0, 1, and then it will start getting steeper and steeper very quickly. This, in fact, is actually the shape of the graph for any number with then x as the power. It always goes really shallow on the left and really steep on the right and passes through 0, 1, because anything to the x power of 0 equals 1. The important thing there is just to get the shape and to quote that coordinate. If instead we were to then draw the graph or the line of ln x, that is going to be the inverse of this, basically mirrored in the line of y equals x. So instead, it's going to look something like this. So it's going to get very close to the y-axis on the right, but never touch it. It'll then cross the x-axis at coordinates 1, 0, and then it will kind of level off into a horizontal, going perpetually onwards to the right. So just indeed, if you had to sketch the graphs, they would have general shapes such as these. On to examples of how to properly solve these logarithms though. If at first we had 8 to the power of 2x plus 1 equals 24, we want to solve for the power, so we want to bring the power down. With that in mind then, we will take a log of base 8 of 24, and that will equal the 2x plus 1. This log base 8 of 24 you will find is approximately 1.528, so that equals your 2x plus 1. Therefore, 0.528 will equal 2x. Therefore, approximately 0.264 will be the value of your x. Here, there we have the log of base 2 of 11y minus 3 minus log base 2 of 3 minus 2 log base 2y equals 1. Now, if we're going to solve for the y's here, we're ideally going to get a single logarithm term here. We can't undo the log like we have done here in this example with the log base 7. If there's multiple log terms, you need to bring them together into a single one. We have minuses, so we know we can use the division rule. However, we need to have the same coefficients. So we don't want this 2 in front. What we're going to want to do is take this 2, remove it from the front, and bring it inside as a power here. So that is now y squared. With this in mind, we can now say that this together is going to be log base 2, and then the 11y minus 3 divided by the 3 and the y squared together, because both of these are being minused. This therefore equals 1 here. Now it's a single log. You can reverse the logarithm, get rid of the logarithm. So this 2 here to the power of this 1, which is just going to be 2, that will equal what was inside the brackets. So 11y minus 3 over the 3y squared. At this point, it's just rearranging and solving. So if we times up the 3y squared here, you get 6y squared equals 11y minus 3. Bring everything onto the left-hand side. 6y squared minus 11y plus 3 equals 0. This you can then factorize into 2, which will be 3y and 2y. And then the 3y will be followed by a minus 1, and the 2y will be followed by a minus 3, because 3y times 2y is 6y squared, 3y times minus 3 is minus 9y, minus 1 times 2y is minus 2y, so the minus 9y minus another 2y gives you the minus 11y, and then minus 1 times minus 3 will give a positive 3 at the end, this equaling 0. Therefore, you'll have either y equals a third in order to make this bracket equal 0, or y equals 3 over 2 to make this bracket equal 0. If you wanted, you could double check and rewrite out the original, just using these as y values consistently each time, but try it twice, and then you should find that those indeed equal 1. What if, though, instead of having a value at the end, we just have another algebraic letter, and instead we're just going to be rewriting some expressions in terms of that letter. So we have that log base 3 of x equals a. Now find in terms of a, first of all, log base 3 of 9x, and then log base 3 of x to the power 5 over 81. Well, here, because these are multiplied inside the bracket, we can use the reverse of this addition rule here to split that into log base 3 of 9, add log base 3 of x. Log base 3 of 9 you could find would equal 2, and then the log base 3 of x we know has a value of a, so it's just 2 add a. As for the other one, we can use the reverse of the minusing rule, so this will be log base 3 of x to the power 5 minus log base 3 of 81. Because of the power rule, we can bring this power out in front to give us essentially just 5 log base 3 of x, and because the log base 3 of x we know is a, that will be 5a, and then minus, you could find that log base 3 of 81 is going to equal 4, so 5a minus 4. If we're happy with that, we can see how we can employ these different rules to both create and then manipulate logarithms to find values for unknowns in various different parts of an equation. Let's just see how you could get along with an example of your own. What if we had that v equals 17,000 e to the minus 0.25 t plus 2,000 e to the minus 0.5 t plus 500. Find, first of all, v when t equals 0, and then the exact value of t when v equals 9,500. Yes, this is a slightly larger expression than what you have been dealing with. This is a kind of question that you could describe potentially as modelling. It would come as part of a bigger question with a larger scenario. I've kind of just cut it down to the bare bones equation here. Even so, just think how we might employ these different logarithm techniques in this question. Hint, you may not be using the logarithm straight away. You may actually want to look to see if there's any other trick we can use first, if necessary. Pause the video, just have a think about it for yourself, and then press play again when you're ready to compare. So, If first of all we're looking for v when t is 0, to be clear, because t is likely referring to time, they may not have told you this, they may have actually said the initial v. If it says initial, that means that t is 0, just to be clear. Either way though, we'll get that v equals 17,000 e to the minus 0.25 lots of 0 plus 2,000 e to the minus 0.5 lots of 0 plus 500. If you were to put that in a calculator, you would find that v equals 19,500. For the second part of the question, though, this is where those tricks of manipulating this equation are going to have to come in. What we may wish to do, because right now we're not going to take logs of everything just yet, because we'd have to take a log of the whole side, and that means the additions would already be inside the brackets, not on the outside, so we couldn't use this rule here. What we want to do instead is maybe actually just give a little bit of a substitution, just to make things a little bit more obvious for ourselves. We'll take the term with the unknown power, so in this case, let's say the e to the minus 0.25t, and let's give it a different value. Let's just say x. With that in mind, therefore, e to the minus 0.5t is going to be x squared, because it's double the power here. Therefore, this up here, we end up with v equals 17,000x plus 2,000 x squared plus 500. And actually, we can already say that that is going to equal 9,500. Bringing that onto this side, you end up with, actually, I'll just put them also in descending powers. So 2,000x squared plus 17,000x minus 9,000, because 500 minus 9,500 minus 9,000 equals 0. What we have here is a hidden quadratic. This term here was a squared power of this thing here. We can actually simplify this by just cancelling through by a factor of 1,000. So this would just become 2, this just becomes 17, and this just becomes 9. This can therefore be broken down into two brackets. We end up with 2x in one and x in the other to times together to make 2x squared. And then what we'll have is we'll have plus 9 here and minus 1 here, because then the 2x times the 9 is 18x, minus 1 times x is minus x, so 18x minus x is the 17x, and then the minus 1 times 9 is minus 9, this equaling 0. Therefore, to make either one of these brackets equal 0, we either need x equals a half or x equals minus 9. Now we mustn't forget, however, that these x's are actually this e to a power term here, and it's t you're actually trying to find. So we end up with e to the minus 0.25t equals a half or minus 9. To solve for t, we would then be taking a natural logarithm, the natural log, because it would be to base e. So ln of either a half or minus 9, except it can't be minus 9, because we notice here we cannot take a natural logarithm of a negative number. It exists only in the positive region here. So in fact, we're going to reject that possible value here. Mathematically, from above it works, but then not practically in the rest of the expression. So the ln of half is going to equal minus what is essentially a quarter t. So if you were to divide by minus a quarter, that would be essentially the same as doing minus 4 lots of the ln of a half. If you wanted, you could bring this minus 1 essentially in as a power. So you have 4 lots of ln and a half to the power of minus 1, which would just be the same as 4 ln 2, which I suppose, strictly speaking, would be a simplified form because it doesn't have a fraction in it. This is the exact value of t. If you were to put that in a calculator and get a decimal, your calculator, even if you didn't think you were, your calculator would inherently be rounding, so it wouldn't be exact. Exact means keep it in the e or the ln form. If that's clear, let's just have a look at one other exam question which similarly could be described as modelling. So we have here now a graph of the log base 10 of v against t, and then this line L is a straight line. So we're told that this is the value of a rare painting, and it's modelled, strictly speaking, by the equation v equals pq to the power of t, where p and q are constants to be found, and t is the number of years since the value was first recorded on January 1st, 1980. The line L illustrates the relationship between t and log of v since that time, and the equation of the line is the log v equals 0.05t plus 4.8. With this in mind, to four significant figures, find the values of p and q. Well, we need to find out what p and q are. They're related to this equation here, but as it stands, we wouldn't have any information to guide us from that. Instead, what we're going to want to do is compare to the other equation that relates v and t. But this has a log in it, so let's see what we can do to try to introduce logs to this. If originally it is v equals pq to the power of t, and you want to make it log v, well, let's log base 10v, but if you log one side, you need to log the other, so that then becomes log 10pqt here. Now these are two things multiplied within the log bracket, so if we want we can split them up into an addition, so log base 10 of p plus log base 10 of qt, and this t we could then also bring out in front as a power, or to power becoming a coefficient. So log base 10 of p plus t lots of log base 10 q. We now have an equation for log base 10 of v, which is the same as over here, only now it's in terms of p and q. Because of this, we can now just compare values. This here is 0.05 being times by the t. Because these are the same equations as each other, supposedly, you can look at what t is being times by here, this log base 10q, and we can therefore say that this must equal the 0.05. Therefore, q is going to equal 10 to the power of 0.05, and therefore q, if we do as the question suggests, to four significant figures, would be approximately 1.122. Then doing the same for the other term, so this 4.8 on its own, that must be the same as this other term here that's on its own, so therefore that will equal to 4.8. Therefore p is going to be 10 to the power of 4.8, which makes p again to four significant figures approximately 63,100. Now that we have these, I want to say, with reference to the model, interpret the value of p and the value of q. Well, p, that is obviously taking the place of this kind of coefficient here of your q term in the original expression. If t was to become 0, so it's q to the power of 0, that would make that value 1. Therefore, all you'd be left with is essentially v equals p when t is 0. That means that p is saying that the initial value of the painting. So originally this painting started off with a value of £63,100. Then, as for q, that would be the proportionate increase of the value each year. So basically each year you take your initial value and you times it by q every single time, so whatever the value of t is. So P is the initial value, and then Q is the proportionate or the proportional increase of that value each year. Okay. And finally, find the value of the painting as predicted by this model on January 1st, 2010, giving your answer to the nearest £100,000. Well, here, now that we know what P and Q are, we can just plug a t value in. Given that we know that it started in 1980 and this is now 2010, that's 30 years later. So we'll say that V equals approximately 63,100 times by 1.122 to the power of 30. And if you plug that into your calculator to the nearest £100,000, you should get a value of 2 million.